chapter 1 seems like a good place, I suppose. With chapter 1, a reminder that the lecture notes are up there on Canvas if you want to use them and print them. And once again, I'm going to be recording these and be writing on the tablet, so you can, everything will be up there for you to see if you want to. Remember that we do sort of use a book that's Adam's first approach, so we kind of jump right into the atom, and that's really what this chapter is going to be about. We're going to talk about some of the experiments that led to the understanding of the structure of the atom. We'll also talk about towards the end there some properties of atoms like mass number, atomic number, and those type of things. And at the beginning, we'll talk about a little bit of some introductory type of stuff for chemistry. So let us get going on it. So really, the main challenge of chemistry, and really what chemistry, for the most part, is pretty much all about, is really matter. And matter really is anything that sort of occupies space and has mass. So it's really a lot about matter. And again, anything that occupies space and has mass is pretty much the definition of matter, which pretty much encompasses most everything for the most part. A lot of what we look at, obviously, in chemistry is how sort of matter changes and how it goes through chemical reactions, how perhaps it resists chemical reactions. And a lot of time, we look to try to see what is happening on the microscopic level to see what is going on. When we talk about matter, there's really three states of matter that we commonly come across, and that is solid, where everything, again, is literally and usually packed in pretty tight to one another, which is why, right, solids are rigid. An exception of that, as we'll talk about in later chapter as well, is water. Water in its solid form is actually less dense than, say, in its liquid form. We have liquid, where everybody is, again, in there relatively close to one another. There's a little bit more room for movement. That's why liquids are fluids. They're able to sort of pass each other in their sort of situation. And then we obviously have gas, which is basically where everybody has broken apart. We have molecules that are flying around. As they're flying around, there's collisions that occur with the container. That's what we associate pressure with when we talk about gases. A lot of what we talk about in terms of chemistry as well is the transitions that occur between these different states. So a lot of focus on phase transitions. When we go from solid to liquid, that is the process of melting, right? Like when you melt an ice cube. When we go from liquid back to solid, that is the process of freezing. When we go from liquid to gas, that's the process of evaporation or vaporization that occurs. Going from gas back to liquid, that is the process of condensation. And we can go from solid directly to gas, and we can skip the liquid phase, and that is what is known as sublimation. We also can go from gas actually back to solid as well, and also skipping the liquid sort of phase of that, and that's what is known as deposition. So a lot of what we look at in a lot of situations is matter really changing these phases, going from one phase to the next. A lot of times, although we don't really talk about it in this class anymore, since they take it out of this class, everything to do with energy, and that's all been moved to 200B. But normally we would talk about energy. So we'll talk about it a little bit as we go through some of the chapters, because frankly, your book imagines that you read that chapter in the book about energy. But a lot of this has to do with energy to do these type of transitions. As we go from, say, solid to liquid to gas, do I need to put energy in to do that? Do I need to take energy out to do that? What do I need to do with energy in terms of that? Energy needs to go in to do that, right? So energy has to be absorbed to do that. If you think about a very simple example of like an ice cube, if you take an ice cube out, right, it picks up all the heat and energy from the surroundings. It starts to melt. If you have liquid water and you want to make some pasta for dinner, right, you put some fire underneath that, it will start to boil, right, which will take it from liquid to obviously the gas phase and so forth. So all of these processes as we go from solid to liquid to gas, thank you, is processes that absorb energy. And when we absorb energy, those processes are what are referred to as being endothermic. Endothermic. Right over here. Endothermic. The opposite is true as if we would do sort of the transitions going from gas to liquid to solid. In those cases, we have gas molecules that are flying around and going crazy, and they have a lot of energy, obviously. So we have to remove the energy from them. And as we remove the energy from the gas molecules as they're flying around, they no longer have as much energy, which means when they do collide with each other, they are going to frankly kind of stick to each other, and they're going to kind of fall out of sort of the air, if you will, and back into the liquid phase, which would create condensation and liquid to occur. If we continue to remove energy, like putting our liquid water into the freezer, it sucks out all the energy, right, to the surroundings. And we will end up getting everybody coming back into the solid phase. They no longer be able to kind of move past each other, and they will lock themselves into that solid sort of rigid phase. So all these processes require, as you go from gas to liquid to solid, sort of in that order, is all processes that release energy. And when we release energy, that is what is referred to as being exothermic processes. Now, again, like I said, they sort of, not really sort of, they've taken out energy out of this glass. So one way that we represent energy in chemistry a lot is through a value. We'll do it here, I guess. Yep. We represent energy in the form of what is referred to as delta H. All right, so delta H is what is known as enthalpy. And enthalpy is basically the heat of a reaction. And it's oftentimes when we're in chemistry, how we sort of look at energy in terms of a reaction. And if you have a delta H value for a particular reaction that is positive, that indicates that the reaction is endothermic and energy is being absorbed. If you have a delta H value that is negative, that means that overall energy there is being released, and it would be a exothermic reaction. So we will definitely see those values in certain chapters. Like I said, the book assumes that you read the energy chapter sort of in the order as the book was written. So when you do see any really in general energy sort of notation that's positive, it's going to be endothermic and absorbing energy. Anything where you have a delta H that is negative, it's going to be exothermic and releasing energy. Now, before we move on from this here, when we have the processes of something like melting and freezing, do they occur at the same temperature or different temperatures? Do those occur at different temperatures or the same temperatures? They do occur at the same temperature. So, for example, something like water at 0 degrees Celsius, where it freezes and it also starts to melt exactly at 0 degrees Celsius, which is sort of the normal melting point, freezing point there for something like water. You actually have both phases happening at the exact same time. So you got some ice, you got a little bit of liquid water, for example. Not really till you get a little bit above 0 degrees that you have liquid water, not till you get a little bit below 0 degrees that you have ice happening there. And the same thing over here where we have evaporation. Evaporation and condensation, that also occurs at the same temperature, and that would be the normal boiling point for a particular substance is where that happens. What makes a determination as to what sort of happens at those temperatures is what is happening with energy. So if you're continuing to put energy in, for example, at 0 degrees Celsius, you will continue the process of melting until you get to liquid water And if you continue to put energy in at, say, 100 degrees Celsius for water, you will continue the process of it boiling and going through evaporation. And obviously, opposite would happen if you continue to take energy out at those points. But if you will take a look at it in a later chapter, but exactly at those points, sort of a plateau line in terms of temperature and stuff like that. And that's where those phase transitions occur. And we'll also talk a little bit about it. And again, you'll talk more about it in 200B since they moved the energy into that class. But there's a certain amount of energy required to do nothing more than just simply change the phase of a substance, not change the temperature or anything like that. The heat of fusion is what is used to kind of take something from solid to liquid and backwards at the exact melting point temperature or freezing point temperature. And the heat of fusion is what is used to go from liquid to gas at the boiling point temperature, not change the temperature or anything like that. Maybe in the previous class, you did a little bit of specific heat action. Yes, maybe Q equals MS delta T. That is used to calculate the change in energy in a substance when it actually stays in the same phase. So a lot of times things like heat of fusion, heat of vaporization are used in combination with the specific heat sort of processes. Because as you will learn in terms of energy, it's basically additive. It doesn't matter how many steps it takes to get somewhere. You just add up all the energy along the way. Talk a little bit about atoms and molecules, which obviously are a big part of what we talk about in chemistry. Matter, as I mentioned, is basically anything that occupies space and has mass. Atoms are really the basic representation of all the elements we have, right? So any element that we have, really the basic unit of it is an atom. And as we'll definitely talk about in this chapter, atoms obviously have an internal structure which contains protons, right? Neutrons and electrons. Now, a molecule is the definition of basically two or more atoms that come together. So molecules is sort of like a basic definition of basically all you need is two or more atoms that have come together. Those atoms could be from the same element. Those atoms can be from different elements. It doesn't really matter, but you just need to make sure that you got two or more atoms that have come together to have a molecule. Now, sometimes people get a little confused about molecules and compounds, right? Now, a molecule, as I mentioned, is a combination of a minimum two or more atoms that come together. A compound is the combination of two or more atoms of different elements. Different elements that come together. So that is really a main difference between those two. It has to be different elements that come together, atoms of those guys, to make a compound. While a molecule, it doesn't really matter. It could be different elements, it could be the same elements. That's the definition of a molecule. Now, some elements do come as molecules. There are a certain number of elements in their uncombined form that are actually molecules. And you should be aware of these, like H2, N2, O2, F2, Cl2, Br2, and I2. All of these guys come basically as twos. This is naturally how those guys come when they are uncombined with each other. And they are sometimes referred to as being diatomic molecules. Di meaning two atoms, right? And they're made up basically two atoms. So something like H2 obviously is two hydrogens together. Something like oxygen, a couple of oxygens together. Nitrogen, obviously, a couple of nitrogens together there. Now, each of those things are diatomic molecules, which clearly means they are molecules. And they are also elements as well. And they are elements because each of them are composed of only the same element, right? Hydrogen has two H's, oxygen has two oxygens there. So they're both elements and they are also molecules. Are those guys in boxes compounds? Those guys in boxes are not compounds because they are not made up of two or more elements, right? So they're all made up of the same element, and that's why they're still considered elements. Every other element on the periodic table there comes as what is referred to as being monoatomic, which means they come as ones, basically. Something like water, which we see here, H2O. H2O is a compound. It is a combination of two or more elements together. You got hydrogen, you got oxygen that come together. Water is also a molecule because it meets the definition of at least two atoms that are together. And obviously water is not an element because obviously it's a mixture of a couple of different elements together. So obviously it is not an element in that particular case. So you can think of, like I said, molecules as sort of like a basic definition of just simply, I got two or more, boom, got a molecule. And if you got a compound, it's got to be two or more, but they got to at least have two or more different elements involved. Any questions on that there? Now, speaking of the periodic table, and we're talking a little bit about it here, and we'll obviously touch more upon it as we go through different chapters. But when we take anything from the periodic table, and I'm sure you know that things have charges in certain cases, do they have a charge? So like if I had a piece of sodium metal, which normally makes a +1 charge, would it have a charge if you just take sodium off the periodic table by itself as a piece of sodium metal? The answer is no. Nothing on the periodic table has a charge when it is by itself uncombined. The only time things get charges is when they come together, and that is when metals and non-metals come together. And as you probably know, and we'll talk about again, it is usually the metals that give away the electrons and become positively charged cations. The non-metals pick up those electrons, become negatively charged anions, and that is when those things actually gain charges. But if you have anything like iron metal, copper metal by itself, uncombined, there really is no charge associated with it. That's a good thing to keep in mind. Yes, sir. Yeah, so this is an example of two things. This is an example of diatomic molecules. And diatomic molecules don't necessarily have to be two of the same element. You could have something like CO, which is two atoms together. But these are also considered elements as well. So they're molecules, but they're also elements because each of them are made up, obviously, of only one element. And this is a thing to remember that, when you see something, for example, in words, like it says, molecular oxygen reacts with molecular hydrogen, you should write H2 plus O2, not like H plus O. Yeah, because when they're by themselves, they do come as those two guys together. Other questions? Yes, they are definitely diatomic molecules, and they could also be classified as elements as well. Other questions? And again, diatomic molecules, like I said, doesn't necessarily have to be an element. Something like CO, carbon monoxide, is also a diatomic molecule. It's obviously two different elements together. So it would be a compound as well. Now, obviously, when we write formulas in chemistry, right, we use subscripts to represent how many atoms of each element are present. So obviously, when we write O2, the subscript always goes to the guy to the left. That means obviously we have two hydrogens, we have two oxygens, you got a little H2O action, you got two hydrogens. When nothing is written, it is assumed to be one because nobody writes one, and we would have one of those guys there to the left. Now, chemical reactions is obviously a lot of what we deal with, and we'll talk a whole chapter, I think, about balancing equations, writing equations. But in general, most chemical reactions have an arrow. On the left-hand side are reactants, which are the starting material. And on the right-hand side of the arrow, it's basically what is formed as a result of the reaction. And those are our products on the right-hand side, what is formed. And throughout different types of reactions, you will sometimes see a lot of stuff maybe written on top of the arrow. Sometimes, a lot of times, they like to put things like catalysts, which speed up chemical reactions a lot of times. Sometimes they'll put something maybe like water to indicate that you're dissolving something in water. So sometimes the arrow there is used to put everything that you see here, put an electrical current. And that's what happens when you run an electrical current over water. You do the electrolysis of water and you actually break it back down. And that's something we'll talk about as well. But we have water on this side, which are compounds, which we run an electrical current, which is basically a chemical reaction that occurs, and we make the elements on the other side. So one thing that's important to remember is you could have compounds and you could do some type of chemical reaction or chemical change to break those compounds into elements. But once you get to elements, that's as far back as you could go. You cannot break those guys apart into anything other than what they are. They stay obviously what they are. Any questions on that there? I hope so, unless I hit the wrong button, but I'm pretty sure it's going to be. I promise. All right. Now you're giving me anxiety, like maybe I hit the wrong button or something. All right. All right, it's only my 10th lecture of the day. It's okay. I'm pretty sure I hit it right. I'm okay. I'm gonna check. Yes, there's been a time I forgot to put the microphone on. Or halfway through, I like shut the microphone off and then I forgot to turn it back on. So there's like a nice recording and then there's a nice silence and just things flashing on the screen. I just go, you can just, imagine what I'm saying at that point. All right, so let's talk a little bit about the scientific method. Science is the framework, obviously. The scientific method really all starts with observations. And that's usually what sort of kicks off the whole events is, maybe you observe something that occurs and you think about, why did that just occur? Why am I seeing that? If you happen to be working in a research lab, you maybe go tell your professor of what you saw. And then your professor says, nice observation. Go do some work now. Go do some experiments and stuff like that. So once you make an observation, typically what's followed is some type of hypothesis. Hypothesis really is, right, a tentative explanation and a testable sort of explanation of what you observed. And that's sort of the key part of it, especially sort of in this process here. You want to come up with some type of hypothesis where you can test it, do some type of experimentation and stuff like that. So that, again, usually leads yourself to some experiments, which unfortunately, or maybe fortunately, it oftentimes will lead you back to more observations. Maybe you get lucky and you observe what you wanted to observe, but maybe you also observe some other things and you're excited and you go tell your professor that and he says, nice observation, go do more experiments to find out why that's happening, right? And it's like a vicious cycle sometimes. And at some point through the process of observations, maybe revising some hypotheses, more experimentation and stuff like that, a couple of things can sort of come out of that. You could end up with perhaps a theory. You could also end up with perhaps a law that could come out of some of the experimentation. And there sort of is a difference between those two. When you have a theory really is sort of a model to sort of explaining what you're observing. It may not be 100% correct in all aspects of it, and it may actually be revised or thrown out, if you will, or later sort of disproven by more experiments that have been done down the road. So, for example, we will talk about Dalton's atomic theory, which, some parts of his theory is still good. Some parts really don't apply still as well. We'll also talk about Bohr and his model of the atom there, theory of the hydrogen atom, which works really well for hydrogen, but as soon as you get a few more electrons involved, not so well. So, that's sort of the idea of a theory. Opposed to that is really a law, and a law does sort of summarize really what happens. And the difference between sort of a law and a theory is a law is pretty much like it always happens that way, and we're sort of convinced that this is always the way that it occurred. So we have something like the law of conservation of energy. We also have like the law of conservation of mass, and it always sort of occurs that way. When we think about sort of the law of conservation of energy, energy is really thought of as sort of, in a lot of cases, like a perfect transition of energy. And what I mean by that is, there's really two things we think about, the system and like the surroundings. system can be whatever you're working on, like your beaker. Everything else could be the surroundings. So if there's something that gives off a certain amount of energy, there will always be somebody that will basically accept that amount of energy. A very simple example would be if you lit the Bunsen burner, you got a flame. The flame is giving off energy, right? That energy is not just disappearing anywhere, right? It is going into the surroundings, right? The surroundings picking up all that energy and sort of a perfect transfer of energy. Law of conservation of mass, right? Also why we sort of balance equations when we have the coefficients. That means, for example, if on the reactant side we have 6 carbons and they break apart all their bonds, they reassemble on the product side, you should still have 6 carbons. They may just be in different compounds along the way. But because carbon is like 12 grams, you got 6 of them, that's a lot of math at this hour, like 72 grams or so of carbon you should have that you started with, because you still have 6 carbons at the end, right? You should still have 72 grams of carbon that should be there, maybe in another form. So the difference between a law and a theory, again, is a law is really something that always should occur the exact same way. It never should really change. It's very, very predictable. This is how these things should happen. A theory, again, is something that can be sort of revisited, revised. Maybe, again, parts of it work well, parts of it later found not to work so well. Any questions on that there? All right. Let us get into some of the chemistry and the beginnings of chemistry, and hopefully roll into some of the atom. Really, a lot of chemistry all started way back when there with Greek philosophers. Robert Boyle is sometimes considered sort of the first chemist. He performed a lot of quantitative experiments. Quantitative means what? Yeah, so quantitative does mean numerical measurements, some type of those type of sort of observations, if you will. And that's different than qualitative, right? Qualitative is more observations that's going on, right? It's like, hey, it turned purple, there were some bubbles, I got to precipitate that formed over here when I do that. So if you take 200B, you do a bunch of experiments, not as much as you used to, but I used to do a bunch of experiments called qualitative analysis, where that's pretty much all you did. You don't calculations, no real measurements. In fact, you don't even measure out the solutions. You just add some drops here, some drops there, a little more drops, and a little less drops and stuff like that. And you observe what happens, basically. Colors change, precipitates form, precipitates maybe go away. So quantitative experiments is really, what a lot of science is based on, obviously, taking measurements, recording what's happening. As I mentioned before, 3 really important laws. We talked about a little bit of some of these here. The law of conservation of mass. Again, mass is not created nor destroyed. We have sort of that in a normal chemical reaction. We do have the conservation of elements. So in chemical reactions, we do have those elements to stay. Like my example I was just talking about, if you had 6 carbons, you should end with 6 carbons. No carbon should take a vacation along the way there in a chemical reaction. Now, is that the case in, say, nuclear reactions? It is not the case at all. You have no conservation of elements. And in nuclear reactions, again, in 200B, you'll talk about it. In nuclear reactions, it's all about basically the protons and neutrons that change. And we do get different elements that occur in that case. In a typical chemical reaction, as we will talk about or in this class, it really involves electrons, which are sort of on the outside of the atom. So it's just the electrons that change, bonds breaking, bonds making, and that never ever will change really the elements that are involved in those type of reactions. The law of definite proportions means that a compound always contains exactly the same proportion of elements by mass. So for example, right, water H2O has basically 2 hydrogens for every 1 oxygen. And since oxygen has a mass of about 16 grams, hydrogen's about 1 gram. So it's like 2 grams of hydrogen and 16 grams of oxygen. That means for every basically 1 gram of hydrogen, you got about 8 grams, right, of oxygen that is present there. So no matter where you get your water, there's always sort of that same proportion by mass that always occurs. Same thing, carbon dioxide, there's 2 oxygens for every 1 carbon. And again, that's basically 32 grams for every 12 grams that you got going on. And that's always the same ratio for each of those things in terms of by mass. And that's the molar mass that's where those numbers come from the periodic table. In addition, the law of multiple proportions, which was done by Dalton, basically says that when 2 elements form a series of compounds, the ratios of their masses to the second one when they combine is always the same and can be reduced down to a whole number. So you probably remember maybe from the previous class that when you put together, for example, a positive ion and a negative ion, you want to put it together in a way where you end up with no overall charge, right? The positive guys balances out the negative guys. And you want to do that in the simplest whole number ratio way of doing that. And that's basically what this is talking about. Atoms, the different elements come together really in whole number ratios. You don't get like a half atom coming in or anything like that. You know, you got a whole atom coming in, and they always can reduce down in most cases to sort of like their empirical formula, if you will, as we'll talk about in a later chapter. Basically, the simplest whole number ratio of sort of what's present is what everything can come down to. You know, even though you have like, say, C2H4, which is 2 carbons for every 4 hydrogens, you know, the simplest whole number ratio of that would be 1 carbon basically for every 2 hydrogens in terms of mass. So that's really the whole number ratio of what's present. They both basically have the same composition by mass, regardless of which one you take, the C2H4 or the CH2. They're both basically the same percentage of each of those elements are present. And you can, in a lot of cases, reduce everybody down to simple whole numbers. All right, so we're going to talk now about some experiments that led into our understanding of sort of the current model of the atom. And as we go through it, we'll talk about, you know, kind of what you need to know for sure, but you do need to have some idea of some of these experiments and stuff that we're going to talk about, and really sort of what comes out of each of these experiments. Really, the first sort of big idea in terms of the atom was one done by Dalton. His name looks like it got caught up there. So John Dalton, which is this guy right here, he showed unusual talent for math. He would keep the record of the weather every day. He never married. Seems interesting. All right. But he did like to go bowling on Thursdays, which is like a super important fact that you should know for sure. And it will appear like on every exam. So like, don't miss it. Don't say Fridays. All atoms. And there's several parts to Dalton's atomic theory, and we're going to talk about each of them here. He said that each element is made up of tiny particles he called atoms. He also said that atoms of a given element are identical to atoms of a different element and are different in some fundamental way. So this is one of the things about Dalton's atomic theory that is not so correct still today. And it's really this part of it here, that atoms of a given element are identical to each other. And the existence of isotopes basically kind of disproves that there. Isotopes are pretty much the same element, but they have different numbers of neutrons. And that means they obviously have different numbers of neutrons. They also will have a different mass because of that. So clearly they're not identical to each other. Another sort of part of Dalton's atomic theory, and as we were talking about earlier, again, this is a theory that again was sort of later disproven. Some parts of it is the idea that atoms are sort of indestructible. You know, you can't really change them into something else. And again, the existence of isotopes, nuclear chemistry sort of disproves that as well. You definitely can shoot some neutrons, protons, and other particles at atoms, and they get very unhappy and they sort of change into new elements in nuclear chemistry. Again, that really doesn't happen in traditional chemical reactions like we deal with in this class, but in nuclear reactions, they do as well. Other parts of his theory are chemical compounds are formed by atoms of different elements, which obviously is what our definition of a compound are. A given element or compound always has the same relative numbers and types of atoms that are present. So obviously, if you have water, you should always have a couple of hydrogens and an oxygen together. If you got carbon monoxide, you should have a carbon and an oxygen that are together. He also thought that chemical reactions really only involve the rearranging of atoms, changes in the way they are bound together, which is really, what does happen in chemical reactions. As I mentioned earlier, it is the electrons and the bonds that are really being broken and being changed as a result of those things. So you should know the different parts of Dalton's atomic theory. You should know, which parts are still sort of correct, which parts are not really correct. Any questions on that? And clearly he went bowling on Thursday. Good, very good. The atoms themselves are not changed in the chemical reaction either. Now I'm gonna forget to put it on the test, and then you're gonna go like, where was the question? That's the only thing I studied. All right. Which is the right way to study, by the way, for the class, is to do that. All right, so let's take a look at these and see here. Which of the following statements on Dalton's atomic theory are still believed to be true today? Elements are made up of tiny particles called atoms. That sounds good. Yeah, so that would probably work. Still good. All atoms of a given element are identical. That would be not so good, right? A given compound always has the same relative numbers and types of atoms. That sounds good. And atoms are indestructible. Again, those are really number 2 on this question. Number 4 on this question are really the 2 things that are still not really correct today. The other ones are. Any questions on that there? All right. That's good. It agrees with me. That's good. All right. So a couple other sort of theories or laws. And again, we'll kind of come back to some of these in some later chapters. Guy Lussac's and Avogadro. These are actually a couple of sort of gas laws, if you will, and gas sort of ideas. Guy Lussac, he measured basically under the same conditions of temperature and pressure, the volume of gases that reacted with each other. Basically, as the temperature went up, the pressure would go up, and as the temperature goes down, the pressure goes down. And usually in that situation, you have actually a fixed volume, so the volume cannot adjust to allow the pressure to change or to stay maintained and not change and stay constant. So because that volume is locked into place, as you raise the temperature, a lot more collisions with the gas molecules, and we get to see a higher pressure occur. And again, as you sort of lower the pressure, the gas molecule is going to be moving around a lot slower, and a lot less collisions are going to happen, and we start to see the pressure drop. Avogadro, under the same pressure and temperature, which we'll talk about, which is often sometimes referred to as Avogadro's law, not his number, but his gas law. And the Avogadro's gas law there basically has the idea under conditions of pressure and temperature, which are constant, basically the number of moles of each of the molecules that are there will be pretty much the same as the volume that's in there. And what that allows you to do sometimes is actually do more of a kind of mole to mole relationship instead of that, like you do in stoichiometry. You could actually do sort of a volume to volume relationship the exact same way as you do a mole to mole relationship. And again, we'll touch more on this when we get into that later chapter. All right. So just to kind of finish up here a little bit about Dalton, this is sort of how he pictured, again, the sort of combination of different atoms. And you can really think of elements, right, as sort of like the alphabet. There's still, I think, only 26 letters, I think. But you could differently arrange, obviously, those letters and make a bunch of different words and stuff like that. And it's the same idea here with really elements and atoms. Although you may have the same sort of combination, if you will, of different elements coming together, based on how many you have of each of those, you will have things with different properties. So like NO, NO2, and 2O, they all are basically a combination of nitrogen and oxygen that has come together. And based on who's in the center, who's down there, each of these things do have some relatively different properties based on the numbers that are present. So based on Dalton's atomic theory, a couple of things were thought of. The atom was really, as I mentioned, sort of defined as that basic unit of an element that really can come into chemical combination. A lot of investigations were done from the 50s, 1850s to the 20th century. And it demonstrated that although atoms are extremely small, they also do have sort of an internal structure, and they're made up of what are sometimes referred to as subatomic particles. And we have our three favorites here, which are electrons, protons, and neutrons. Electrons, as you may know, and as we will talk about, are negatively charged particles. We have protons, which are positively charged particles. And we have neutrons, which basically have no charge in terms of their particles. They are obviously found in different places within the atom, and we're going to talk now about some of the experiments that help us sort of discover some of these, discover some of the sort of properties of each of these guys, and where they are basically found within the atom. So really the first major set of sort of experiments that led us to really a better understanding of the electron were the experiments that were done by J.J. Thomson. J.J. Thomson did a lot of work with what is referred to as a cathode ray tube, or CRT. That's for cathode ray tube. You may be familiar with cathode ray tubes, maybe. You're maybe still young enough. If you ever seen maybe a older TV, a older computer monitor, anything where the back of it kind of comes out, those are all basically cathode ray tubes. Definitely not flat screens or anything like that. That's not going to work or anything. But those are CRT tubes. And basically how it works is sort of a simple idea, and a very important idea in terms of chemistry is the idea of opposites attract, right? So much like in life, opposites attract in life, right? You don't want to be maybe two positive people together. That's got to be annoying at some point, right? So nobody wants that. That's just too happy of a situation, maybe. Two negative people, well, they won't want to be together either, right? So what they always say, opposites attract, right? You need like a positive person, negative person to maybe balance each other out. And the same thing happens sort of here in chemistry as well. And almost a lot of all types of attractive forces and things that we talk about in chemistry and how molecules interact with each other is this basic principle of if you have a positive thing and a negative guy, they are going to be really attracted to each other. And that is the whole basis of ionic compounds, right? You have a positive ion, got a negative ion, and they're going to be attracted to each other. And the same idea for a lot of things like why we have different sort of geometries or molecular geometries for molecules is it's all about electrons. And when electrons get near each other, they're both negatively charged. So they don't really want to be near each other. So they try to move away from one another as best as they can. And so things with like charges, they sort of repel each other, right? And positive things don't want to be near each other, but these guys are obviously attracted to one another. So in a cathode ray tube, for the most part, there is sort of a positive plate and a negative plate. And we have a beam of negatively charged guys, which are really like electrons, and they would be heading towards the positive plate there because they're attracted to it, and obviously away from the negative side there. And the effect of this is it allowed a lot of experiments to be done using things like electrical fields, magnetic fields, which can take advantage of particles that have charges. So for example, if you had a electrical field where you had something that was positive, you had something that was negative, and you shot a beam, and that beam sort of headed upwards towards the positive side, we would know that that beam most likely has what type of charge? Negative charge. If you shot sort of particles and it sort of bent down towards the negative side, we would know that this guy would be more of a positive one. And if you shot something and just kind of sailed right through and really wasn't attracted to either way, that thing would have basically no charge. So a lot of early experiments and later experiments as well really do take advantage of this idea of opposites attract to allow certain things and experiments basically to take place. So Thomson did a lot of work with the CRT tube, which looks just like my drawing. So this is a CRT tube. I know, I failed art 4 times. It's all right. So here's the negative side. Here's the positive side. And again, that beam of negatively charged particles are heading towards the positive guy. In the old days, in the old TVs, that was your picture tube that went out, and the guy could come and kind of play with it with a magnet and dial it in and to try to fix it and stuff like that. Yes, you used to call people to come to your house to fix your TV. You didn't run to Costco and just get another one off the shelf or anything like that, right? And throw your old one away. There's a whole industry of people that would come, they rip the back off of your TV, you know, get in there and fix it. Lost industry, these things nowadays, right? Everything's disposable. We kind of get rid of it and buy new things, right? That's why there used to be vacuum repair shops, right? People would actually fix their vacuums and stuff like that. All right. That's a life lesson I just gave you. You're welcome. It's free of charge today. So he did a lot of work with this cathode ray tube. I know I'm entertaining myself, and I think that's the important part of this lecture. Right? So there is Thomson staring at his cathode ray tube, which brings me to, I know, another thing out of the past that maybe they don't say anymore, but the parents used to tell you, don't sit in front of the TV because you're just being shot by something, right? And you're being shot by a cathode ray tube usually, not anymore because you got flat screen. So you're all right, I think, these days. But what really came out of his experiments, if we get back to chemistry for a bit here, I think, what really came out of his experiments with Thomson was he was able to really figure out the charge to mass of an electron. So he was able to figure out the charge to mass of an electron, and that's the important thing that came out of his experiment. And he came up with, right there, the number of minus 1.76 times 10 to the 8. A C is a coulomb. It's a unit of electrical charge per gram. So the first thing that you should know is early work that was done on electrons was done by Thomson using the CRT tubes to have a little understanding of what a CRT tube is there. But mainly you should also know that what came out of it was he was able to determine basically the charge to mass of an electron. And this was really good because kind of the next important sort of aspect in terms of an electron was another experiment that was done by a guy named Millikan. And Millikan did what is commonly referred to as the oil drop experiment. And Millikan did this oil drop experiment where, much like the name implies, he shot some oil into a chamber. And in this chamber, he had an electrical field going on, little hole for your oil droplet. So he shot the oil droplets in here, heated it up really good, atomized it. And what would happen is you would expect the oil droplet to start to fall based on gravity. As it obviously starts to fall, picks up some charge and all that good stuff as it does that. What he was able to really do in his experiment was he was able to really adjust the electric field in such a way that basically he was able to sort of suspend the oil droplet there without it falling, obviously, or going up or down, and sort of suspend it. And what he was able to basically do some calculations and determine was the charge on an electron. So Millikan did this oil drop experiment, and the main thing that came out of it was the charge on an electron. And that's really important if you think about kind of the two experiments together. We have Thomson with his CRT tube that came up with the charge to mass of an electron. We have Millikan that came up with the charge of an electron, which means actually if you take the results of both of those experiments, you take the charge and you divide it by the charge to mass of an electron, charges will cancel, and that will allow us really to determine the mass of an electron. So these two experiments were really important as it led to a really nice understanding of the properties of electrons, but also the mass of electrons when you take them both together. And if you do that sort of calculation there, you're able to get the actual mass of an electron. And I think we have it on the next page here. So let's take a look here. I think there was the charge on the electron. And again, a worse picture than what I drew, I think. But if you want a little bit of a worse picture, you can take a look at that one. That was sort of the setup there. Again, the oil droplets came in here and started to drop, adjusting the electrical field, allowing the oil droplets to kind of hang there. So using those two numbers together, as I mentioned, allows you to calculate the mass of an electron. And there is the number right there. The mass of a single electron there would be 9.09 times 10 to the minus 28 grams. Is that a large number or a small number? That's a pretty small number, right? It's like 28 places to the left, right? Put some zeros in there, 27 zeros there to the left. So it's a very, very small number, but that is the result really of these two kind of important experiments. So at this point, you should be aware of those two experiments, Thomson and CRT tube, Millikan and his oil drop experiment. Thomson charged a mass of an electron, Millikan charge of an electron. The result, using both of those experiments, the mass of an electron can be found. Any questions on that there? So let's talk about the proton then and the nucleus. So by the early 1900s, there was a couple of things that was sort of understood by everybody. And the idea there was obviously from these early experiments with the CRT tubes and also the Millikan experiment that atoms did contain electrons. They were also believed that atoms were electrically neutral, which means if they did contain electrons, they had to have something else there that basically is a positive charge to balance it out. So around sort of the turn of the last century there, the accepted model of the atom was the one that was proposed by Thomson. And Thomson's model of the atom is basically was referred to as the plum pudding model of the atom. And basically the idea was that we have a sort of spherical atom where all the positive charge is pretty much diffused over the whole sphere. And sort of embedded inside the sphere is where we find our electrons. So we have these electrons sort of embedded inside. So the plum pudding is like a dessert of like pudding with some raisins sort of embedded inside. So he thought the raisins were like the electrons, and obviously the pudding there is the positive charge that's sort of spread out. He also felt that most of the mass of the atom was the electrons. So this again is sort of an early model of the atom and sort of an accepted model of the atom at this present time during sort of the course of these experiments. And here's a much nicer picture of that. Again, you can see the electrons embedded inside the positive sphere. And this was really the accepted model of the atom till really the next major sort of event that occurred in terms of experiments, and that was Rutherford and his gold foil experiment. So Rutherford did a gold foil experiment where he shot alpha particles at pieces of gold foil and other metals. Alpha particles are radioactive particles, so alpha particles are positively charged radioactive particles. They're really helium, basically. I really like the helium nucleus. By the way, there's a couple other important radioactive particles. There's beta particles, which are negatively charged. These are beta particles. They're kind of like really an electron. And then there's also gamma rays here. And gamma rays are really just kind of pure energy, if you will. No charge. So these are three sort of important radioactive particles that were used in a lot of experiments. And, you know, they really do, if you think about it, sort of mimic what we find in the atom at the end there, kind of like positive guys like protons, negative guys like electrons, and the guys with no charge that are kind of like neutrons. So they really do mimic it. But the nice thing about these particles are they are charged particles. So they are affected by things like electrical fields, like we were talking about before. Again, if you shot these particles through sort of a field, you would expect sort of our beta particles, right, to sort of bend that way, our alpha particles to come that way. And obviously our gamma guys are just going to kind of shoot straight across and be unaffected. So what he did was he took pieces of gold foil, and really he thought the atom was sort of based off of Thomson's model, which is his plum pudding model. So he was going off the idea that we have this model of the atom where we have all this positive charge in it. We have all these electrons that are embedded in it. And he thought that when he shot these alpha particles, basically, which are positively charged radioactive particles, they're moving pretty good and moving pretty fast. He expected them to really kind of go through with some deflection for sure. And if you think about it, like if this was our atom, right? I know it's kind of rectangle at the moment, but if this was our atom and this was all the positive charge really spread out all over it, and if I held one side of, say, this atom and somebody held the other side, and we shot like a pin at it, right, moving really, really fast, it most likely would be able to kind of hop through, right, with a little bit of deflection and go through, especially obviously if both sides are really, really tight. And that's sort of what he expected to happen when he shot these alpha particles at these atoms. He expected them to go through, but since they're going through sort of a mushy, really spread out positive charge, and these guys are positive charge, because they're moving so fast, they would be able to go through, but there would be some deflection and kind of curvature, if you will, as they go through, because they are sort of like charges. So you have sort of a setup such as this here, and you have a source of alpha particles back here. You got your gold foil here, which is really a bunch of atoms, right? It's basically in the piece of gold foil. Some type of screen there where you can kind of see where everything's hitting. And what they found was really kind of surprising to them. They found that when they did shoot these alpha particles at it, for the most part, they went straight through with no deflection, which is why you can see the thickest sort of beam there going kind of straight through. But what they did see that was also kind of surprising to them when they did this experiment was every so often they would see an alpha particle kind of scatter at a large angle. And that's why we see some hit over here, we see some hit over here, over here, over here, over here. And frankly, you have some coming back where it's coming from as well. So every so often there would be these alpha particles that get scattered at these pretty long distances. But for the most part, they had no problem. Most of them just kind of sailed right through with no problem. And that was very surprising based on sort of their idea of what the atom looked like at that time. They definitely expected it, pretty much most of them, to be sort of deflected and not just kind of going straight through. So they compared it to sort of like shooting a gun at a piece of paper, and some of the bullets obviously coming back, and the same idea there to have those alpha particles come back. So that brings up really two sort of questions. The first question is, obviously, if most of the alpha particles went straight through, what did it hit? So what did it hit if it went straight through? That is a trick question. It didn't hit anything because it went straight through, right? It just headed straight through, and there was nothing in its way. It's able to go straight through. And that's basically why it went straight through, was it hit nothing. So there had to be pretty much some empty space for it, right? Otherwise, if it hit something, it would have bounced off right at large angles. But we did see some of these alpha particles bounce off at large angles. So some of these guys were able to do that. So what did these guys hit? What would they have to hit to make that alpha particle bounce off at a really, really large angle? They would have to hit something that is what type of charge? Yeah, because alpha particles are positively charged. In order to make them bounce off at those really large angles, it had to hit something that was pretty much solidly positively charged to make it bounce off at those really large angles. You go back to my wonderful paper demonstration of the atom, and instead of the positive charge being spread out over the entire sort of area, if you took all that positive charge and you folded it, what do they say? How many times can you fold before you can't fold anymore? 8. That's 2, 3, 4, 5, and I'm not going to go any more than that, but I'll try to. So something like that, right? So if our positive particles here, our charge is not spread out over, but really, really concentrated here. If I then take my alpha particle and I shoot it at it, right, it's going to bounce off at a large angle. It's like a 3D show. I know, it's okay. Sorry about that. Thank you very much. Oops. Thank you. So that was really the two major things that came out of this experiment. They found out that, you know what, the plum pudding model may be not so correct here. It clearly doesn't have this positive charge spread out all over. It definitely does have a very, very concentrated positive charge that is there. So on the left, here's the picture of what they expected to happen. And this is what actually happened here. And you can see that it did have this positive charge here. And that accounts for why we see these alpha particles spreading out at, or bouncing off at these really large angles. The ones that really just kind of sailed through really didn't run into too much there. So what does this mean? This means that, frankly, they had to sort of reimagine the atom. And they first had to go back to our plum pudding model and go, not so good. So they had to sort of toss out the plum pudding model and come up with really an explanation based on what they found. And they explained that the nuclear atom, for the most part, was filled up with empty space. And again, that's what accounts for pretty much most of the particles having no problem sailing right through. They also accounted for that in the atom, there is really this center core, which is known as the nucleus, that is obviously very, very positively charged, which once again accounts for why those alpha particles are scattered at these really large angles. And what they also discovered or determined was probably in that empty area or empty space, that's really where you have your kind of electrons sort of moving around. What we sometimes refer to now as sort of like the electron cloud is where everybody's kind of flying around in the atom. And the last major difference between the two models was this. In the plum pudding model, they thought that the electrons was pretty much the majority of the mass of the atom, and they no longer believe that at this point. They believe that it's actually the nucleus that made up most of the mass of the atom. So this is really the modern version of the atom, where we have basically a very positive core where we have our nucleus, and later on in 1930s, we know we have our protons in there, which are positively charged. And in the 30s, we also know we have neutrons that have no charge. Both are obviously found in the nucleus. We have all this empty space where electrons are out and about from the nucleus at some distance. We also eventually will find, obviously, that electrons do not move in pretty circles. Electrons move pretty randomly about that sort of empty space where the nucleus is. And as we'll also talk about, you really don't know at any given point in time exactly where an electron is or how it's moving. It's just going to be a good probability of finding an electron, either a higher probability or a lower probability of finding an electron in some location. So you do need to know a couple of things as before we kind of finish up talking about this. You do need to know, obviously, Thomson's model of the atom, the plum pudding model, what it was made of or out of. You also need to know Rutherford and his experiment. Rutherford shot alpha particles at things, not expo pins. Can't tell you how many times I've had the expo pin answer on the test. I enjoy that answer, by the way, but not what they shot. Again, much like the bowling, I don't think they had the expo pins back there either. But he did shoot alpha particle on it. So you need to know his experiment and obviously what he expected to happen. and obviously what actually did happen, and now obviously sort of the modern version of the atom. Any questions on any of that there? All right, so we have a little bit more things to sort of fill in. This table here kind of goes over the experiments we just talked about and sort of what came out of those experiments. So it's a nice little summary table of, kind of what we talked about up to this point. We found through experiments that the mass of a proton is 1.67252 times 10 to the minus 24 grams. And if you remember, that is about 1,840 times heavier than any electron that there is. If you remember, the electron was like 909 times 10 to the minus 28 grams was the electron. So this is a much smaller number than obviously this. When you compare exponents that are negative, the smaller negative exponent is the larger number, right? Because you're going less places to the left. So at this point, scientists basically perceive the atom as a nucleus, basically comprises most of the mass of it, although it's really, really small. So, you could think of like the atom itself, like this Superdome, and maybe like, the nucleus is like on the 50-yard line there. If you ever been to the Superdome, very, very big. And the seats are like this. Like you feel like you're falling out of the seat as you're sitting in it. They're so tilted because they're on such an angle and stuff like that. So I know these are just extra things. I know, it's all right. It's all right. So the protons are confined to the nucleus while the electrons are spread out from the nucleus. Is there any type of attractive forces between the electrons and the nucleus? There is, right? Electrons are negatively charged, right? The nucleus, for the most part, is positively charged. So back to that opposites attract. So although the electrons are moving about in a random sort of motion, they are sort of tied to the nucleus through that attraction. And some electrons are tied to the nucleus a lot more than others, which is why only certain electrons are involved in things like bonding, like valence electrons, which are the guys furthest away. The core electrons, which are right there kind of near the nucleus, they're held super tight, so it makes it very hard for them to leave or sort of interact in sort of a bonding sort of situation. So the last sort of subatomic particle was really not discovered until 1932, and it was always thought of that, there really was something else sort of in that nucleus besides the protons. And the proof of it came in 32 by a guy named Chadwick. Did a lot of work with sort of X-rays, and they really had sort of no charge. And they found out eventually that there were neutrons, and they had a mass of 1.67495 times 10 to the minus 24. The reason for the lots of points here is that just barely edges out the proton, and the neutron is actually the heaviest of the three subatomic particles. Proton is just slightly less massive than that. It is also about 1,800 or so times heavier than the electron as well. So in terms of the subatomic particles, it is the neutron that is the heaviest, followed very closely by the proton, and it is the electron that is the lightest of the three particles. Do you need to know the masses of each of the particles? The answer is no, but you do need to know that the neutron is the heaviest, followed closely by the proton, and the electron actually is the lightest. Now, those masses also sort of reinforces Rutherford's idea, because he basically said that most of the mass of the atom was the nucleus. And clearly in the nucleus, you have protons and neutrons, which means both of those guys are pretty much the heaviest particles you could have. And each of them individually are about 1,800 or so times heavier than any electron. So it does make sense that most of the mass of the atom would be made up of the nucleus, because that's where we have our protons and our neutrons basically housed. Any questions on that there? Yeah. They are. Yeah. Other questions? Yeah. There's a table of the mass of the three subatomic particles. We have our protons, electrons, and neutrons. And like I said, you don't necessarily need to know the numbers. In fact, it may even be provided to you, but you do need to know, again, sort of the order of, you need to know the order of which one is the heaviest to the lightest. You also need to know, obviously, the charges of each of those, and you need to know where they are found in the atom. Yeah. Any questions on any of that there? So, in case you're not sure from our conversation, one last time here, electrons found outside the nucleus, negatively charged, flying around in that sort of empty space. Protons positively charged, found in the nucleus, and neutrons also found in the nucleus and no charge. So the nucleus, like I mentioned, small compared to the overall size, but very, very dense and positively charged. And here's sort of that cross view of the atom. Again, that sort of red area is what is sometimes referred to as electron clouds, or that empty space. We have our electrons sort of moving around in that area, and obviously our nucleus, they're very, very small. So I think that is a good place to stop, I think. So any questions on anything we talked about here today? You need to know, once again, the experiments that we talked about and highlighted. You know a little bit about the experiments, what came out of them. You need to know the plum pudding model. You need to know the modern Rutherford model, if you will, and obviously Rutherford's gold foil experiment and what came out of it. Any questions on any of that there? Yeah. All right, so what we're going to do is lay it up there for right now.